Fabio and Suyash, and hello everyone. It's really a great um, honor to have this opportunity to share some of my experience using the Gleeble over the last almost 30 years now. And I hope that you guys would have some questions after the presentation so we can discuss. Because my way of doing these kind of things always trying to be a mutual way, two ways, not just one way. Okay, so the title I'm going to present, you guys already know, it's called Gleeble Platform Best Practice, because Gleeble is the one that the people you guys are using, and I hope that you guys will use the well and better. Okay, so I'm going to provide this into four subjects. First one is the Gleeble Platform of Materials R&D, and the Gleeble Working Principle, and a test design, and a data application. Because after all, we want to apply the data into your problems or project. So when we talk about a Gleeble platform, I really want to address again, anytime I doing this kind of talk, that is Gleeble is not a testing machine. A testing machine like MTS Intron is just a tool that you need to do nothing but follow the standard, right? You don't even need to think. It's just there is a standard there, American, India, or European or Chinese, they just follow, right? But Gleeble is different. It is not a testing machine. It is a platform on which you can do lots of things. And I will share some of the things with you so you would understand how powerful the Gleeble is. Okay, so let's focus on first on why I call it Gleeble is a platform. We'll take steel processing or steel manufacturing as an example. I believe everybody knows what a steel is, but this process is very complicated. I won't say it's the process itself is very expensive, but the product is very cheap. I mean, as cheap as probably you can buy a vegetable from your market, right? But such a complicated process, and we can make it so cheap now in terms of product price. The good reason is that over the years, we have studied so many problems, and the Gleeble honestly is a very important role in this. We all know that Gleeble can do everything from casting downstream to the end product, even during service. And I'm going to tell you very soon that the Gleeble can also do melting the casting as well as composition determination. So that way you will have a very powerful tool to do whatever really you want for new materials research and development. Because after all, we know that there are only two things that can determine the final product in terms of property or service. One is a composition, and the second is processing. With all the Gleeble you have now, you can do all kinds of processing to optimize microstructure and properties. But after all, composition is the key. So I will tell you later how we can do even the composition. Okay, so back to the steel. Okay, now such a complicated process. Every step, every critical step that we see, Gleeble can be a powerful tool to study it. No matter if it's casting or rolling or even forging or even strip annealing or even welding or even the strength and the property during service. Right? No matter what kind of material it is, if it's a tube, strip, or a beam, anything. So that is why we need to call Gleeble a platform, because that way every user that can fully use of your own brain to make this a powerful tool for your research and development. Because the great thing is the researchers are always the people who are leading the technology in the world. Now, with that saying that, I still want to address, why we needed to do physical simulation. We all know that, but I want to adjust it in terms of these 4 points. Firstly, we can develop new alloys, right? And we even for the current materials, we can optimize it because you don't know if there is any room to improve. And honestly, there's always a room to improve. And then for the production process, even though it's producing, the right dimension product, but they may not be the optimized property or optimize the schedule. So we can optimize it, we can improve it, we can crack the problems such as cracks that we might see in the real process. And of course, we can use this to shorten the development time, no matter for R&D or for new materials development. So this is why we needed to do physical simulation to help our industrial process. Okay, and then how we do it. Again, this slide is not new. Lots of people have seen it, but what I want to see is everything we do is really into the industrial process, right? Everything you develop has to be processed to make a product that can be useful. The way we do is usually we do in the lab on Gleeble to do all the physical simulation to improve the process, develop new alloys, as I say. However, we have to be aware that now computer modeling is a very, very powerful tool now that you cannot ignore it. Over the years, computer has been improved so much, and the computer modeling is so powerful that even a physical simulation itself cannot really help as much. For example, when we do welding simulation, we especially the HEZ zone, right? We only know a certain point in the HEZ zone in terms of its microstructure or property. But when you really want to know the whole HEZ zone's microstructure and property, it's tough. So you have to use a mathematical model like a FEM model or differential model to help to give you a 3D field. So this slide tells us that when you want to attack some of the problem in the real field in terms of temperature distribution, strain distribution, or microstructure distribution, or even is there any potential for cracking, you needed to combine the computer model. So with the combination of the computer model and the physical simulation, you can do all kinds of things. That's what I'm trying to say. So again, come back to the Gleeble platform. We can do lots of things. And again, this slide is not new. Some of you guys have probably seen this already. But I wanted to cover these 3 areas. One is the basic material studies. The second is the material testing and the metallurgical process simulation, because these are all the things that the Gleeble can cover. So I'm not going to go through all the details. We'll show you some of the things that people are being studied using the Gleeble, such as phase transformation, oxidation, liquid metal. I'm not going to go through all of this. If you guys need it, you can come to make a copy of this. But again, these are all the very basic material studies that you can do using the Gleeble, like melting, superplasticity, hardening, softening, crystallization, recovery, precipitation, even ultra-fine grain materials, as well as nanometer materials. Testing, I want to say it again, this testing is not MTS or instrument type of testing, because we don't have standard. There is no standard in the world for hot activity, for hot workability, even a cycle procedure. There's no standard. It's just a testing technique that you can use for your research, for your problem solving. Uniaxial, it's very, very popular testing, but honestly, there is no standard in the world. Plane-strain compression, theoretically, there is no plane-strain compression at all, because obviously there's a limitation on the specimen side there. But we call it plane-strain compression. Dynamic CCT, every steel researchers or some materials researchers will need it, because that is the role that you have to know how it's going to affect your final microstructure, right? And the weldability. Gleeble is born by welding. So weldability test is just so easy and so popular. thermomechanical fatigue, elongation, and some elastic module, yield strength, UTS, all this. You can do it. Creep, stress rupture, stress relaxation, and the plane strength fracture toughness test. These are the testing I just make a list that you can use to help you to do your research. And the process simulation, as I just mentioned, we can do everything from casting downstream, okay, including semi-solid processing, TMCP, welding, as I said, upset butt welding, friction stir welding, and friction welding, diffusion bonding, any kind of heat treatment, because we can heat 10,000 C per second, and then we can cool at the 10,000 degrees per second too, with such a wide range. What a heat treatment can I do by Gleeble? Strip annealing. Everybody is making sheet metals, right? 70% of the steel market is really made of sheet metals. Powder metallurgy, sintering, and hipping for high temperature or exotic materials, synthetics. So all the things you can use the Gleeble can do. So there is a really very limited limitation of the Gleeble you can do. That is the idea I want to address today, very, very seriously. That is why I called the machine, the Gleeble, as a platform, not the testing machine again. Now, the proof is this, the data. No matter what I say is what I say, but data is data. Look at this data. The number of papers that has been published over the years has been increasing exponentially. What does that mean? Everybody is using the Gleeble to make their research work. Everybody would love to have the Gleeble to help them to do all the R&D work. So look at it, from 2010 to 2019, we have found like 14 or 15,000 papers that published on the net, and that's just partial of it. We all know that all the paper published by all these professors, research institute researchers. Dr. Kumar probably could publish like 1,000 papers using the Gleeble, but he can't because the cell would not allow him to publish any paper, right? And the same for the other student producers. So and this is just a partial, but it tells us that everybody's using Gleeble to do all the research because it is a platform, as I said. All right. Now we'll come back to the basic, because we are using the Gleeble. We want to use the Gleeble as we just said, how powerful it is. So there is something very important every Gleeble user has to understand. I didn't say that you don't understand, but I'm saying I want to repeat to make sure that some of the people who do not know then will know after this presentation. Gleeble itself as a thermomechanical simulator is not really that difficult at all if you understand the principle. After all, there are two basic loops. One is the mechanical loop, right? And tension and compression. That's it, nothing else. If you have a mogul valve, hydraulic valve, you can do the tension and compression, no matter what it is. Very simple. Of course, if you want to make a high speed, then there are some tricks. That's why Gleeble is different. MTS is so easy. So slowly doing. Everybody can do it. But when you running like a 2 meters per second, it's not that easy because you have to control well, right? But it's simple. The principle is very simple. Just right tension and compression. Or if you guys need to do torsion, we can put a hydraulic torsion motor on it. They're the same thing. But the thing different from all the other testing machine is the thermal loop that DSI's Gleeble has. Okay. Well, when talking about thermal loop, it's simple. Again, you just have a delta T, right? You measure the temperature and give the computer another temperature. If there's a delta T, then we'll just open the circuit to heat the sample. Otherwise, we'll shut down. So the principle is very simple. The delta T is always the driving force. But the key here is this: how can you control the thermal gradient in your specimen? So we know in the electrical circuit, right, from the transformer to the specimen, it's a really electrical circuit. And I'm telling you that with the DSI, the Gleeble thermal loop, the secondary voltage is only 12 volts. And the voltage between the jaw, two jaws from one to the other is about 6 volts only. However, depending on the resistance of the circuit, including the specimen, you can check into lots of current. So with the Joule heat R square R, you can generate very high heating rate. And of course, you can keep the specimen at the steady temperature, which means the heating rate is 0, right? So going back to this thermal gradient issues, because when we do the thermomechanical testing or thermomechanical simulation, the thermal is the most important part. That's why I put thermal ahead of the mechanical, right? We didn't say mechanical thermal simulator. Because, or even some people even have thermal simulator, because thermal is so important. And when we do thermal, we need to know the temperature field or temperature gradient. And this is all you see. And I'm telling you this is slide, okay? I would consider is the most important one of all that you can see from the Gleeble. Okay, now in this slide, you guys see that there are only two type of testing. One is the tension, one is the compression. That's all what a Gleeble can do, right? And now for the tensor testing, when we using the tensor testing system as an example, okay, actually the compression one is the same. If you look at the electrical circuit, there are lots of resistance in there. And in this test setup, we have 5 resistance. We call it 1, 2, 3, 4, 5. Right? R1 is the resistance of the temperature. R2 is the resistance between the sample and the grip. And R3 is the resistance of the grip itself. And R4 is the resistance, what I mean is electrical resistance between the grip and the jaw. And R5 is the resistance of the jaw, which is made of aluminum alloy, just to let you know. You cannot really do nothing about this. But for R1 to R4, you can change it to control the thermal gradient as you wish. Okay, you can change in R1, R2, R3, R4 by doing lots of things. For R1, you can change the specimen diameter, length, or free span. For R3, you can change in the materials, Gleeble material from copper and stainless or half contact. That is why you guys have so many different set of grips. So what I would like to suggest is do not just simply pick a grip to do the test. You have to select what grips that you have to use for your research. It's just not a grip fits all. No, okay. And the same for the compression testing. We have R1 to R5. By changing R1 to R4, you can change really the temperature within the specimen. For example, for uniaxial compression, you need to make sure the temperature from one end to the other is the same, because that's one of the 2 factors that you are making a uniaxial compression test. So that's why I'm saying by controlling R1 to R4, you can achieve the thermal gradient control for your testing. Okay, that is the one, and I'll give you an example. Look at this. If you see the right upper right corner, the temperature distribution from one end to the other of the jaws or the free span, we can make a specimen very uniform, like the one you see in the left corner. It's like a furnace heating, right? But Gleeble is so powerful, you can control the thermal gradient over the axial direction, or I call it the axial thermal gradient. You can make it very steep, like the one on the left bottom corner, because these are the situations that you see in the real world, right? In the welding, in the rolling and forging process, you see thermal gradient everywhere. If you don't consider thermal gradient into your research, your test will be misleading. So you have to consider all the factors that you see in your real process into your testing. Okay, but the good part is that Gleeble can control thermal gradient, and the thermal gradient is so important. I put on here because as you see in this one, these are 2 types of materials that you can see. The top one is a 1018, very simple plain carbon steel. The bottom one is a 304 stainless steel. But you look at it, okay, you will see that the reduction area is different from left to right. yeah, for both materials. But you got to notice these specimens are tested under these two same conditions: 1000 C, 50 millimeter per second. Okay. If you really don't pay attention to it, you thought, okay, well, if the temperature is the same, the stroke rate is the same, then the ductility, everything, strength will be the same. But you see, it's different. Why? Because we have a different thermal gradient in the material, in the specimen. That is why you see lots of cracks at the corner or edge of your steel billet, no matter if it's in forging or steel rolling, because the corner, it has the largest surface to volume ratio. And with that, you have the steepest thermal gradient in the billet. That's why you get crack easily, because of the thermal gradient. Okay, so you need to consider thermal gradient when you do any kinds of cracking issues if you want to study. And the same thing for the strength. As I just said, you would think the strength is only dependent on the temperature and the strain rate. Nope. Look at this. At the 1000 C and the 50 millimeter per second, the strength is almost doubled from 9 C per millimeter to 283 C per millimeter. Almost double. Look at it from UTS stand, and the elongation was even almost 5 times different. Crazy. That is how Gleeble can help you guys to do those kind of research. The MTS would never be able to tell you all this at all. So I put this on the thermal gradient in there just to let you guys pay attention when you do the test. You got to would be aware of this. Another thermal gradient, which is very important too, is the thermal gradient along the radial direction. Lots of people probably know already that in the ingot casting, we will see some of the holes in the center of the ingot. Lots of people probably know already why. Because there is the shell solidify first, right? And sent to solidify the latest. And when we consider doing the melting test on the Gleeble to simulate continuous casting, we need to pay attention to this as well. We need to keep the temperature as uniform as formal, not only in the radial direction, because otherwise you have a good thermal gradient. You may run into some holes in the sample when you see the fracture surface. So how we can minimize the surface temperature to the center temperature, or the delta T between the surface and the center. We need to control the environment. If you look at this data at the 1200 C, we would have almost a 50 degrees C in the environment of helium with carbon steel as a specimen at 1200 C. Okay, so you look at it, when the specimen surface temperature is 1200 C, the center is almost 1250. Okay, if you change the helium to argon, then the temperature difference will be around 30 C. If you do it on vacuum, then go down to almost 20 C. Why? Because on the vacuum, there is no convection heating. But there's still a big radiation heating there, because the radiation is a T to fourth power. Okay, so now for stainless steel in argon, it's less. Why? Because stainless steel's electrical resistance or thermal conductivity is 3 times low than copernicum steel. So it's less conductive. So anyway, we need to control the environment to minimize surface temperature with the center one. How? There are 2 ways you can do. One is you could use the thermal sleeve. You probably already seen that from the IsoTMO assembly. It's an insulating white weaving sleeve. So you can apply the sample to cover the sample, so that will reduce the heat radiation and heat convection. Right. The second approach is that this DSI provides we call it cement. It's a white powder. So when you mix it with water, you can paint around the sample to minimize the heat loss in both radiation and convection. So that way, with that, if we test it, with the thermal sleeve on, temperature difference between the surface and center is only within 2 degrees C. That's almost ignorable, right? So that's the way how we control the thermal gradient in axial direction and the radial direction, so you can know what you're doing. Okay. So now we're back to the test design. Test design is very important. We all know that, because by proper doing the test design, we can achieve the data we need, instead of get some data that are not enough, or sometimes even misleading. So my experience is that if the materials that you are testing or you are studying is not as expensive, do as many tests as you could. For example, Japanese research, Dr. Suzuki at Nippon Steel, when he used the Gleeble to do the castability map, he asked his people to do 3 times for each point that you want to correct, because with 3 tests, if some of the test is really out, trial, then you can just kick it out. Okay, or take the average to make your test data much more solid. Okay, so I would encourage you to do as many as you could if the time and the cost is not an issue, because that would give you a very solid data for your analysis. But when we talk about test design, I mean, it's nothing new. I mean, it's very simple, but I want to address for you attention. Then first, we have to understand why we are doing the test. What a goal you want to achieve. So I call it the objective of the testing. What a problem you want to solve, And then with that, we need to select the right testing technique. As I say, the Gleeble is not a testing machine. There is no standard, but we have so many testing technique. And I hope you guys will help us develop more testing technique to share with the rest of our Gleeble community, so everybody will get a benefit of it. But again, we have already enough testing technique used worldwide for you to pick. So pick the right one, or maybe 2 or 3. Sometimes 1 or 2 is not enough to correct your problems. And then the third one is the number of tests, as I mentioned. The many, the more the better, because it can give you a very confident level of the test data that you are getting. Okay, so I'm going to give you some examples, very simple examples, how you do the test design. It's my experience. This one, some of you probably have seen this already. U-shaped processing of the pipe welding. Normally, it's just a conventional welding process. You just U-shape it and squeeze it together, and then just weld along the straight line. But now this is a new technique. They're using high frequency electrical heating to do the welding without electrode materials at all. I believe it's much more efficient, it's much more economical and fast. But the thing, if you guys can understand very easily, is that it's a heating up of the gap, right? Both sides of the material, and then by screwing the 2 rolls and at the different at the right speed. So it's just a continuous process, nothing exhaustive in there. But the key is what temperature, what speed, what reduction is the best to give you the best microstructure and the property. Gleeble is a perfect tool to do that. Okay, so if we want to study this process, there are 5 factors we have to consider: heating rate, temperature, at the time you squeeze, right? And the reduction, how much reduction we need to squeeze, how fast we need to squeeze, how fast we need to cool, because after all, the microstructure, the property is the one we want to go after. So by doing all these factors together, you can give the processor, this processing operator, a very good idea what is the right temperature, what is the heating rate, what is the reduction, right? And then you will be the heater. And then the testing technique, as I see, for this one, it's very simple. The opposite welding technique is the one that you need to pick, because by doing this, you can simulate all these 5 factors. And right after, you can check the interface stress and interface microstructure. And I put Dr. Wimmerlein here at the BHEL, because when I was visiting him last year, he was doing a great job by joining the stainless steel and the titanium alloy. And as he told me, the strength is better. I wouldn't say it's double. It's much better than their original process, and the interface is just super. And to me, it's just a great. Such a simple test, but doing something so great that can even patent the technique to replace what they are doing. That's a huge contribution from the Gleeble technique, right? The second on the rolling. Rolling schedule is always the first important thing that you have to develop for all kinds of new alloys or new steels you do. But before having Gleeble, let's say, lots of people simply just assign the rolling pass reduction into every pass, determine the to make sure the final dimension is met. But with the Gleeble, we should not do that anymore. We should determine your hot rolling schedule scientifically, because after all, you want to achieve the best materials properties for your customer. So in order to do that, there are lots of at least 5 factors you have to consider it. First, the mill capacity, right? You have to make sure that the mills or forgers can do the deformation you want. Secondly, you don't make sure there is no crack. Nobody likes crack. Thirdly, what is the reheating temperature is the best temperature that you got to use. And then do the roll path design. Okay. Finally, you will understand what kind of mixture you're achieving, because the mixture determines the property. So with all these into consideration, one technique is not enough. I would suggest you need lots of testing. For example, hot ductility, uniaxial compression, double hit compression to do the luxurization behavior. Stress relaxation, you need to study the precipitation behavior. CCT, you need to understand under which conditions, what kind of margin you can achieve. So again, for a problem you want to solve, okay, one testing technique may not be enough at all. You may need to do a combination of the test to make you fully understand your material, fully understand your processing conditions. Only that way can you achieve what you want for your customers. Okay, and then I want to talk about IsoCube, because IsoCube is such a powerful tool to achieve the ultra fast cooling. Because now in steel rolling process, ultra fast cooling is really the new technique. Everybody is trying to use it because they want to control multi-phase microstructure with a good combination of ductility and strength. And without IsoCube, you cannot do this kind of testing. So then with that, as I said, when you do CCT, I mean, lots of people are using, uniaxial compression testing to do the CCT. Or for static CCT, it's okay. But for dynamic CCT, that's not the best choice. Rather, the IsoCube with the CCT, this kind of dog bone shape spacer is the best. You heat up to different temperature, apply different the reduction, strain rate, and then you can cool as fast as you could. When I say as fast as you could, I mean mainly we can achieve 400 C per second from 800 to 500. That is the probably faster cooling, control cooling you achieve in the world. Of course, if you really want to do high, we could still have some ways to do that. But what I'm saying is, by using this kind of technique, you can do lots of good CCT results with the Gleeble. And a sickle, when we first developed the sickle, we called it the strain-induced crack opening. That's where the sickles come from. But now, sickle is not just for crack opening. Sickle can be used in lots of places. Forging simulation is a very, very good quality technique. The weldability determination, as well as some of the forging process optimization. Some of you probably have read a paper on crankshaft optimization developed by Tyson Steel. So sickle is a very good technique you can pick. And on the right side of the sample, I'm telling you, if you does not really define the right processing conditions, every material you can see will crack, no matter if it's aluminum, nickel-based alloy, or some austenitic steel. So this technique is very good. Why? Because the stress state of this testing procedure is similar to what you see in the real industrial processing, like forging and the rolling. Hot tensile hot ductility testing is not, because as soon as you have a necking, the stress state becomes triaxial stress state, which you now see in the real process, but a cycle does. Okay, the final portion is the data application. As I said, we needed to do the test to solve the problems, to develop new materials, right? So data application from the Gleeble to the real industry is really a challenge. Lots of people, ask this question, and the good answer is this: you need to know what kind of data you are getting in order to solve your problem. And again, by Gleeble alone may not be enough. Sometimes you may have to use FEM models to help you to become a powerful tool to solve your problem or research your material. But of course, Gleeble alone can do lots of application directly. Very good example is the strip annealing. What I'm trying to say is that if you can get a good parameter of the thermal processing of the strip annealing, continuous annealing, if you get a good property out of the Gleeble, you can simply just apply it onto the production line without any plant chart at all, because that has been proved worldwide. Of course, there is some other tests which can do the same thing too, but for like a forging piece process simulation, if you want to know the distribution of the microstructure or property, or if there is a potential for crack at any places, Gleeble test alone is not enough. You need to combine with the FEM model to give you a 3D picture of the workpiece during processing. Okay, now that is why that TMS is proposing a roadmap they call ICME, Integrated Computational Materials Engineering, and that exactly is the same kind of idea that we just proposed from DSI almost many decades ago. We needed to combine both to the process, improve the process. So this roadmap really tells something is this. Conventionally, what we do is this: we determine we do the steel, making, let's say, and then to try to make it as clean as possible, and then process it, and I get a final dimension, and whatever property we got, is what you got. But now things has to do the different way, or is the reverse way. Your customer will ask you, is this, hey, Dr. Kumar, can you develop a material that have this kind of property? I want to, the strength is this, ductility is this, a hot, particular strength is this, or this. Can you make it for me? Well, I can tell you now, yes, you could. But how? That is, you, based on the required property that you want, you go reverse way to determine what kind of composition that you have to have, and then optimize the processing using the Gleeble to achieve the property you want. But of course, the process is not that simple, because if you look at this slide, by just using 4 elements, carbon, manganese, silicon, and aluminum alone, 4 elements, you could have like 600,000 combinations for your steel composition. And there's no way that you can test it this 600,000, even though you have unless you have like a million Gleeble in your lab. So AI, artificial intelligence, is the way people are going after now. But again, artificial intelligence is a database supported computer model. So without a physical data, computer model is just an equation. It's useless in a certain way. So you have to use the physical simulation data to support your artificial intelligence database to make you much smarter, system-wise, to help you to decide what kind of composition that you've got to have, what kind of processing condition you have to meet to give the property that your customer is asking, because you have told them that you could. And the good news is that Gleeble DSI has designed a system that can dramatically accelerate and simplify the development and the collaboration of new alloys or new steel. It's super. Normally, it would take a year or half year or at least several months to develop new steel. And it costs you a fortune. But it costs you 5 Gleebles to do a punch high. But now with the Gleeble's rapid system, you can do this, both composition and the processing, within probably days or at the most weeks. It's very, very powerful. And I want to share you with you guys because it's just the way everybody in the world will follow ICME. And this is the schematic design of our Gleeble rapid system. There are 5 modules there. Module 5 is the one that you have already, Gleeble. We call the rapid TMS system, thermomechanical simulator. But the other 4 modules is the one that they can help you to decide the composition. Module 1 is a melt cast. In other words, after you mix the composition, we can simply just melt cast it. If you want to roll it into a deformed structure, you can use a rolling mill or forger. If you want to check the microstructure, after that, you can use module 3 to characterize the microstructure. And then you can machine the samples into the Gleeble one. You can do it. It's all together into a systematic, way of doing developing new alloys. So I hope that you guys will be interested to help you develop new alloy, because after all, new material is a way to lead the industry, no matter the steel or other non-ferrous materials. Okay. So with that, I will conclude my presentation. But before I do that, if you guys feel interested, you can go to scholar.google.com. Yesterday I did a Gleeble search. There's like hundreds of thousands of related papers there, so you can look at it, or Science Direct also. And if you guys have any interest in developing new, technology or new alloy, DSI will be more than happy here to help you. So you can contact any member of our team to do your research. After all, as I just said in the beginning, we want to everyone of our Gleeble users to fully use of the Gleeble as the research platform to help you become the world leader of your research. Okay, so that's my presentation today, a little bit longer than I expect, but thank you very much. If there's any question, I'll be happy, our team will be happy to answer. Be safe, be well.
All right. Well, thank you very much, Dr. Wayne Chen, for this very nice and excellent presentation.